This section is about the limited or finite bandwidth of real op-amps. So far we assume that the ideal op-amp has infinite bandwidth. This means it amplifies signals of all frequencies the same. It also means that there is no phase shift between the input and output. As we shall see later, this means that there is no instability with an ideal op-amp. Instability arises from the phase shift between the op-amp input and output. However, a real op-amp has a finite bandwidth. Above a certain frequency, the gain drops off. And with a real op-amp there is a frequency-dependent phase shift between the input and output. As we shall see later, this gives rise to the potential for instability. This is what the open-loop frequency response of a real op-amp looks like. It has a first pole at 1 kHz, and a second pole at 10 kHz. Normally, the op-amp open-loop frequency response is modeled using a single dominant pole. Also note that this graph shows only the gain as a function of frequency. The phase shift between the input and the output is not shown. We continue with exploring the finite open-loop bandwidth of op-amps. In the previous slide, we explored what a gain versus frequency plot looks like for an op-amp. In this slide we are exploring the same for a real commercially available op-amp. The op-amp we are exploring in this slide is the LMV116 and the LMV118. This is a Texas Instruments op-amp. This is the gain and phase as a function of frequency for the LMV116 and LMV118. This graph contains more detail than the previous. It includes the phase, as well as the effective temperature. Temperature variation has an influence on the gain, but not so much on the phase. At 45 MHz, the phase shift between the input and output is about 150 degrees. The open-loop bandwidth for these two op-amps is specified as 45 MHz. The vertical red line is drawn up from 45 MHz to indicate where the bandwidth is on this graph. As we explore the op-amp, we shall often come across the statement that the op-amp is modeled using a single dominant pole. This is often used in the op-amp stability analysis, which we shall explore in more detail later. In this course we are going to explore both the single and double pole models, as well as their respective performance. Next, we are going to develop our op-amp model to include finite bandwidth. We are going to use single and double pole configurations to develop our op-amp model with finite bandwidth. We start our analysis of the op-amp using a single pole model. This is how the ideal op-amp circuit is modified to include the single bandwidth limiting pole. The circuit is modified further by isolating the output stage from the input stage using a buffer gain stage, eBuff. The total open loop gain is determined by the input stage gain, E-gain, and the buffer stage gain, E-buff. To keep things simple, E-buff is set to 1. E-gain therefore determines the overall open loop gain of the op-amp. In this example it is 1000, or 60 dB. To limit the bandwidth of the ideal op-amp, a single pole is added to our LT-SPICE model. Our pole 1 and C pole 1 with the values as shown, makes up the low-pass network for the first pole. For this example, the pole is at 10 MHz. The frequency of this pole can easily be adjusted to match that of a specific op-amp by adjusting the values of our pole 1 and C pole 1. In this slide, we explore the frequency response for the ideal op-amp with a single pole added. This is what the frequency response looks like for the op-amp circuit in the previous slide. This is the pole at 10 MHz due to the RC circuit that was added. The solid red curve is the variation of the amplitude with frequency. And the dotted red curve shows the variation of the phase shift between the input and output as a function of frequency. This is the LT-SPICE schematic, for the op-amp model with a single pole. It is set up to calculate the frequency response from 0.1 Hz to 100 MHz. The LT-SPICE schematic is attached, and is set up to do a frequency response simulation of this circuit. The name of the LT-SPICE file is shown in the slide. The assignment is to vary the values for a pole 1 and C pole 1, and observe the effect on the frequency response. This brings us to the end of this section. In the next section, we are adding a second pole to the ideal op-amp.